Greetings everyone and welcome to my presentation. I'm Dr. Dibyashree Shrestha, Assistant Professor of Chemistry at Patan Multiple Campus Institute of Science and Technology, Tribhuvan University, Nepal. My research delves into the structural and electrochemical aspects of renewable carbons and composites across various carbonization temperatures with a focus on enhancing supercapacitor performances. This is the overview of my presentation. Before we dive into the intricate details of my research, let's first grasp a fundamental element, activated carbon. This remarkable material, characterized by its porous structure and expansive surface area with various functional groups, boasts a plethora of applications. This slide highlights its diverse uses ranging from environmental remediation to energy storage, notably in supercapacitors. Supercapacitors are advanced energy storage devices revolutionizing energy storage efficiency. They offer a significant advantage, storing 10 to 100 times more energy per unit mass or volume compared to conventional devices, making them highly sought after for diverse applications. Compared to the lithium-ion batteries, supercapacitors boast higher energy density, facilitating more energy storage in a smaller space. Additionally, they charge and discharge rapidly, ensuring quick energy release, have extended lifespan, operate effectively across various temperatures, and are environmentally friendly. Supercapacitors have vague application areas from consumer electronics to backup and UPS system to hybrid vehicles to medical equipments to heavy load operations. Now I would like to talk about statement of problem. There is a lack of clarity regarding how carbonization temperature influences the performance of biomass-derived carbon electrodes for supercapacitors. Despite its crucial role in material synthesis, the impact of carbonization temperature on electrode performance remains uncertain. Comprehensive understanding of this relationship is crucial for advancing supercapacitor technology. Hence, the objectives of this study are to investigate the relationship between carbonization temperature and the electrochemical properties of Terminalia elliptica hood-derived carbon electrodes, addressing existing knowledge gaps comprehensively. We will examine how varied thermal conditions influence the structural characteristics and electrochemical behavior of the resultant carbon materials, with a focus on determining the optimal carbonization temperature to enhance specific capacitance, cyclic stability, and rate capability of carbon electrodes for supercapacitor applications. Through these objectives, we aim to contribute significantly to the development of high-performance and environmentally sustainable supercapacitors. Let's discuss about the thermal decomposition of raw hood powder of Terminalia elliptica hood by TGA to ascertain the carbonization temperature. Here, the thermal decomposition behavior, that is TG curve, confirmed that 400 degrees centigrade was the adequate temperature for carbonization of raw hood powder, since no significant weight loss was occurred after 400 degrees centigrade, which confirms the completion of carbonization process. Now I'm moving on to the experimental part. This is how activated carbons have been prepared. To prepare activated carbons, sun-dried hood waste was finely ground and sieved, and 80-gram powder was mixed with 85% phosphoric acid in a 1:1 ratio and wetted at 25 degrees centigrade for 24 hours. The mixture was then heated. heated at 110 degrees centigrade for 2 hours. The resulting sample was divided into four 20-gram portions and carbonized individually at 400 degrees centigrade, 500, 600, and 700 degrees centigrade for 3 hours each under nitrogen flow. After air cooling and neutral pH washing, activated carbons AC 400 degree, AC 500, 600, and AC 700 degree centigrades were obtained and characterized structurally and electrochemically for supercapacitor electrode stability. These tools have been used to characterize as prepared for activated carbons. Now I'll discuss briefly on the results obtained. First, I'll start with XRD. So the phase state of activated carbons were determined by XRD. The XRD diffraction pattern of the activated carbons prepared at different temperatures are shown over here. Notably, the pattern for activated AC 400 degrees centigrade displays a broader hump at around 23 degree 2 theta, having a plane 200 compared to those of 500 degrees centigrade, AC 600, and AC 700 degrees centigrade. This observation indicates a higher degree of amorphousness in the carbon structure synthesized at 400 degrees centigrade. So Raman spectra clearly displayed D and G bands, and the relative intensity ratio of G and D band was found to be less than 1, that is just 0.97, which also confirms the presence of amorphous nature of the material compared to other activated carbons having G to D ratio greater than 1. So finding of XRD nicely agreed with the Raman spectra that activated carbon AC 400 degrees centigrade is more amorphous in nature. The surface functionality of the activated carbons was determined by FTIR spectra, which showed that prepared activated carbons are well functionalized, having various oxygen-containing functional groups like hydroxyl, ketones, and ether, which are reported to be crucial for customizing activated carbon properties for improved energy storage and delivery in supercapacitors. So this figure shows nitrogen adsorption-desorption isotherms of the prepared activated carbons at 77 K. So here, as can be seen, activated AC 400 degree and AC 500 degrees centigrade gave characteristic type 2 isotherms showing hysteresis loop, indicating the presence of enormous mesopause, whereas activated AC 600 degrees centigrade and 700 degrees centigrade lack hysteresis loop, suggesting a dominance of micropause. So activated carbon at 400 degrees centigrade showed highest surface area of 1434 meters square per gram due to abundant mesopause. Then the surface morphology of activated carbons was investigated by SEM. Activated carbon samples produced at 400 degree and 500 degree centigrade demonstrate clear interconnected pores, indicating successful pore development without collapse, whereas those at 600 degree and 700 degree centigrade shows less defined porous structures due to excessive temperature leading to pore instability. SEM analysis at 20 micrometer magnification suggests that the 400 degree and 500 degree centigrade temperature range is optimal for achieving desired porous structures in hood-based activated carbons, striking a balance between pore creation and preservation for effective production. TEM images reveal intricate pore networks conforming 400 degrees centigrade as optimal for desired porous structure, while temperatures beyond exhibit signs of structural degradation, highlighting suboptimal morphologies for target applications. It was seen that among the four activated carbons, the AC 400 degrees centigrade was found to be more amorphous in nature, highly porous with enormous mesoporosity, large surface area, and contained oxy-functional groups which are vital for supercapacitor performances. Now, our focus shifted to fabricating activated carbon electrodes following structural characterization. Each electrode comprised 8 mg of activated carbon powder, 1 mg of carbon black, 1 mg of polyvinylidene fluoride (PDVF) dispersed in 20 microliter NMP solution. The resulting slurry was applied onto nickel-form substrate, dried overnight at 70 degrees and activated by immersion in a 6 molar KOH aqueous electrolyte solution. So, furthermore, our research explored the creation of hybrid composites by combining activated carbon with manganese dioxide in the ratio 1:1. That is, hybrid composite materials was prepared by combining 4 mg of activated carbon, 4 mg of MnO2, 1 mg of carbon black, 1 mg of PDVF, and 200 ml microliter of NMP solution. Then fabricated activated carbon electrodes and hybrid composite electrodes were subjected to rigorous electrochemical characterization employing cyclic voltammetry, galvanostatic charge discharge, and EIS techniques, aiming to elucidate electrochemical performance enhancement. The conditions applied for electrochemical characterization are shown over here. Now I'm moving on to the evaluation of electrochemical performances of AC electrode and hybrid composite electrodes. I'll start with cyclic voltammetry analysis. This slide shows cyclic voltammogram of as fabricated activated carbon electrodes and hybrid composite electrodes incorporating manganese dioxide at various carbonization temperatures. Cyclic voltammetric analysis of activated carbon electrodes exhibited robust electrical double layer capacitive behavior, that is EDLC behavior with high specific capacitance, while hybrid composite electrodes showed enhanced charge storage due to combined EDLC and pseudocapacitive contributions. Lower carbonization temperatures, that is 400 degree and 500 degree centigrade in AC electrodes, resulted in higher specific surface areas and greater charge storage through electrostatic interactions, whereas hybrid composite electrodes displayed pronounced redox peaks from MnO2, indicating reversible Mn3 plus to Mn2 plus conversion reactions and increased charge storage capacity. Then the capacitive behavior is further investigated by galvanostatic charge discharge at various current densities of 1 to 20 ampere per gram, showing a decrease of discharge time with increase in current density. The galvanostatic charge discharge study compared activated carbon and hybrid composite electrodes at 400 degrees centigrade. Activated AC electrodes displayed distinct triangular profiles characteristic of EDLC with discharge times of approximately 120 seconds for AC 400 degrees centigrade, yielding specific capacitance values of 183.4 farad per gram, whereas hybrid composite electrodes exhibited a bending nature resembling pseudocapacitive behavior attributed to internal oxidation reduction reactions in MnO2, with discharge times for AC MnO2 400 degrees centigrade is 490 seconds, resulting in specific values of 491 farad per gram. Now, let's see the specific retention. The stability of the electrodes were investigated by percentage retention capacity. Long life cycle is one of the vibrant characteristics that an ideal supercapacitor should have. So as can be seen, capacity retention over 1000 charge-discharge cycles at 3 ampere per gram was monitored for activated carbons electrodes and hybrid composite electrodes. All electrodes exhibited an initial stabilization phase followed by gradual decline in specific capacitance after approximately 200 cycles, attributed to material decomposition into the electrolyte during repeated cycling. So here we can see that AC 400 degrees centigrade electrode demonstrated wonderful stability of 96%. Whereas hybrid composite electrodes, particularly AC MnO2 400 degrees centigrade, demonstrated remarkable 99.4% of initial capacitance after 1000 cycles, attributed to MnO2's pseudocapacitive behavior and redox reactions, mitigating material degradation during cycling. Now I'm moving on to electrochemical impedance spectroscopy, which is EIS, which is also called EIS measurements. So EIS measurements were conducted on activated carbon and hybrid composites electrode in a 6 molar KOH solution across a frequency range of 100 kHz to 0.1 Hz, generating Nyquist plots. These plots revealed polarization resistance at high frequencies and capacitive behavior at low frequencies. Notably, AC 400 degrees centigrade electrode demonstrated superior conductivity with remarkably lower internal resistance of 0.43 ohm compared to other activated carbon electrodes, attributed to its higher specific capacitance, facilitating efficient ion and electron movement. Among the hybrid composite electrodes, AC MnO2 400 degrees centigrade stood out with significantly lower resistance of just 0.36 ohm compared to activated AC 400 degrees centigrade, attributed to its high specific capacitance, enhancing ion transport and conductivity. This EIS analysis underscores the advantage of preparing activated carbon electrodes at 400 degrees centigrade, highlighting the crucial roles of internal resistance and specific capacitance in electrode conductivity and providing insights for system optimization. Now let's see the energy density and power density. Energy density and power density were evaluated to assess the performance of storage devices, with Ragone plots constructed based on galvanostatic charge-discharge measurement for AC and AC MnO2 electrodes, that is, activated carbon electrodes and hybrid composite electrodes. Equations incorporating specific capacitance, potential window, and discharge time were used for energy density and power density calculations, which are shown over here. Key findings revealed that activate AC 400 degrees centigrade exhibited the highest energy density of 4.2 watt-hour per kg at power density of 144 watt per kg, followed by AC 500 degrees centigrade grade having having energy density of 3.1 watt hour per kg at 127.4 watt per kg power density. So here the ACMnO2 400 degrees centigrade showed significantly higher energy density of 25.3 watt-hour per kg compared to AC 400 degrees centigrade, emphasizing MnO2 synergy. Both AC 400 degree and ACMnO2 400 degree centigrade demonstrated exceptional energy density and power density values, promising for energy storage applications. Now we have come to the key points of the research. Our study demonstrates the pivotal role of carbonization temperature in shaping the properties of phosphoric acid activated carbons. Activated AC 400 degrees centigrade exhibits outstanding electrochemical performances with high surface area, specific capacitance, and cyclic stability, indicating its suitability for practical applications and suggesting exciting prospects for enhancing energy storage devices through ACMnO2 400 degrees centigrade hybrid composites. Now, my deepest gratitude is extended to the Central Department of Chemistry, Tribhuvan University, and Patan Multiple Campus Institute of Science and Technology, Tribhuvan University, Nepal, for providing essential laboratory facilities and a supportive environment for the research conducted. The research also benefited greatly from the generous support of the Global Research Laboratory at Sun Moon University, South Korea, for their invaluable expertise in material characterization. In Thailand, sincere thanks are offered to the Advanced Functional Material Physics Lab at Suranari University of Technology in facilitating electrochemical measurements. Thank you for your attention.